BCR 4.1 is all about introing nuclear reactions and radioactivity. There are 5 main concepts when we're dealing with nuclear reactions in the introduction of all this. So, first thing is explaining what subatomic particle or particles are affected during nuclear reaction, being able to compare the energy being released from a nuclear reaction to a chemical reaction, understanding what it means for a nucleus to be unstable and how that relates to the balance of attractive nuclear forces and repulsive electrical forces, understand what it means if an element is radioactive, understand the process of radioactive decay, how it affects the atom, and how it relates to radiation. Now, this can seem overwhelming, but I want you to just know that this is a very surface level objective. We're not getting too deep. We're kind of being pretty broad on this and just introducing what nuclear reactions are. So the first thing that we're going to look at are pretty much what are nuclear reactions. Sorry, I'm going backwards here. There are actually 3 main types of nuclear reactions. Nuclear fission and nuclear fusion are things that we are going to hit on the next, in a couple of objectives. That's actually objective 4.4, and you can go out of order. It really doesn't matter with this set of objectives, but that's something that we will focus on later. And then radioactive decay is more what we'll focus on this objective and also in 4.2 when we're talking about half-lives. All of these affect the nucleus. And because they affect the nucleus, they affect the protons and neutrons. And really the protons are what makes nuclear reactions so special, because when we affect the nucleus and when we affect the protons, we can create new elements. And that happens by fusion, taking 2 small atoms, and fusing them or gluing them together. Fission, where we take a large atom and split it apart. And radioactive decay, where we take an unstable nuclei and decompose it, essentially. All of these things have one big thing in common, though. And you can take a look at the bottom right-hand corner of your screen. They give off a ton of energy. And actually, compared to chemical reactions, it's about 100 times more on average than a chemical reaction. So nuclear reactions, because we're affecting the nucleus, a lot more energy, because it takes a lot more energy to do that. Now, what does it mean to be radioactive? And here's kind of the 3 main components. If you have a radioactive atom, or isotope, like we like to call them, it is considered unstable, and we'll focus on what that is here shortly. It will emit radiation, and radiation is just the energy that comes off of radioactive atoms. It's just what's being released during the radioactive process. And then also, it's going to change into another element. So it is going to decompose, or it's going to break down and create a new element that is less unstable than the previous. And maybe it's completely stable, but sometimes it just continues to break down for a couple of different atoms in order to get stable. Now, what is stable versus unstable? So, big thing that you need to know, there are 2 main forces, and we can take a look at those here in the atom. The first main force is the strong force. The strong force is what holds the atom together. This is kind of like the glue, or kind of like a balloon, the surroundings of the nuclei, and the protons and neutrons are held together by the strong force. In most atoms, the strong force is greater. Okay, there's I shouldn't say very few, but most atoms, strong force is going to be greater. It's going to hold it in nice and tight, and there's going to be no issues. The electromagnetic force also is acting on the nucleus, and the electromagnetic force is what is pushing these protons away, kind of trying to pull apart the nucleus. And how that's coming about is because the protons all have positive charges. Well, we know likes don't like each other, and they want to repel. So these protons are pushing on each other to repel. Therefore, the electromagnetic force is pushing away. Okay, so we mentioned that in stable atoms, the strong force is greater than the electromagnetic force. Okay, the nucleus is going to hold still. It's not going to do anything. However, when we get to these large nuclei, we have these unstable atoms. And the reason being is because the electromagnetic force becomes greater. And this is because the strong force, if we go back here, the strong force is really strong at the center of the nucleus. When you get farther and farther out from the center of the nucleus, meaning when we get more and more protons and neutrons and stuff in that nucleus, the nucleus gets larger and larger and larger. Well, then you get farther and farther away from that center point. The farther you are from the center point, the weaker the strong force gets. That's when the electromagnetic force can take over and rip apart the atom or pull apart the atom and decompose it into an unstable nucleus or unstable isotope or atom, making it radioactive. So again, all radioactive elements are unstable because the electromagnetic force is greater than the strong force. Now, what is radioactive decay? Radioactive decay is one of the things that we'll look more at in process, but it's a natural process all day, every day, all around us. One example of this is carbon-14. Carbon-14 is something that is in every living or once living thing, and now that it's dead, it is decaying that. It's decomposing that carbon-14, which is an unstable atom. And when that decomposes, it emits radiation, just like every radioactive decay reaction does. But just keep in mind, just because it emits radiation doesn't mean all radiation is bad for us. Think about all those things that were once living. If those were all bad, then we probably wouldn't be here, okay? And also, radiation can't travel far, and that's a big thing. If you look at this picture, you have the radioactive decay of uranium-238, which is a product typically used in nuclear reactions and specifically fission when we talk about nuclear power plants. So this is going to decay by itself, okay? And when it decomposes, it takes billions of years, but when it decomposes, it will turn into helium and thorium. And what that just means is it broke down. Helium is a stable atom. Thorium is an unstable atom. However, it is more stable than uranium-238 is. So when that happens, it is going to emit radiation, just like all radioactive atoms do. And then it's going to go through its process of becoming more stable by, again, doing the radioactive decay. And it continues through this process until we get to a stable atom along the way. And that could take billions of years. It could take fractions of a second. It just depends on what type of atom you're looking at. The big idea here is in all radioactive decay, all new elements are formed. Because we change the nucleus, we now have new elements because we've separated the protons. When you separate protons, you then form new elements. And before this, we never dealt with the protons. Protons never change. But in nuclear reactions, because we're affecting the nucleus, the protons do change, so new elements are formed. So just to kind of reiterate everything, you need to be able to explain what subatomic particles affected during nuclear reactions. So we're talking about the nucleus here, being able to compare the energy being released between nuclear and chemical, okay, understanding what it means for a nucleus to be unstable and how that relates to the balance of forces, understanding what it means for an element to be radioactive, and understand the process of radioactive decay, how it affects the atom, and how it relates to radiation. Once again, this is a very surface level objective, a lot of content, but not really much depth. So please let me know if you have any questions or if there's any clarification you need. All right, thanks.